Good morning to all dear students. Let us start with the lecture of Algebra 1, Algebra Rings and Fields. In last lecture of Algebra, we have defined normal extension. Now let us prove a theorem related to normal extension. Uh, let K be a normal extension of F. H be a subgroup of GKF. And KH be a fixed field of H. Then we have to prove that number first dimension of K over KH is same as order of H. And the second thing that we have to prove is GKKH is exactly same as H. GKKH is exactly same as H. So these are the two things that we have to prove. Here we are assuming that K is a normal extension of F, and we have to prove these two things. So let us start with the proof. Now what is KH? Okay, KH is defined like this. We know that it is nothing but collection of all those elements of K, which is fixed by every elements of H, which is fixed by every elements of H. That is what KH is, or fixed field of H is. Then by the definition of KH, it is clear that H is a subset of GKKH. Why? Because if we start with an element of H, for example, suppose I start with an element of H, say A belongs to H. Because we know that H is collection of all automorphisms. Let us start with sigma. Any sigma belongs to H. Then I have to show that this sigma belongs to GKKH. We know that elements of GKKH are collection of all automorphisms which fixes every elements of KH. So in order to prove that sigma belongs to GKKH, I have to prove that sigma fixes every elements of KH. Okay, that is, this sigma must fix every element of KH, because the definition of this is all those automorphism sigma from K to K such that sigma fixes every element of KH. This is the definition of GKKH, right? So I have to prove that this sigma fixes every elements of KH, and that is already true because every elements of H are already fixing the elements of KH. KH is in fact collection of all those elements which is already fixed by every elements of H. So one thing is clear that this sigma fixes every elements of KH, and so H is a subset of GKKH. Okay, so that is clear by the definition of in fact KH. So now let us once again go ahead. And because of this, what we have is order of H is less than or equals to order of G, K, KH. And also one thing we note is that we have proved this theorem in last unit that if K is a finite extension of F, then order of GKF is less than or equals to dimension of K over F. This we have proved in last unit that if K is a finite extension of F, then order of GKF is less than or equals to dimension of K over F. So because we know that KH is a finite extension of, K is a finite extension of KH. Is already there. Why K is a finite extension of KH? Because K is a normal extension. So by definition of normal extension, we must have K is a finite extension of F. Now note that KH is a subgroup of K, and also note that KH will contain F. So that therefore this relation is there, that KH is subset of F is subset of KH is subset of K. This kind of relation is there between these three fields. We can easily prove that F is a subset of KH. That means H fixes every element of F. When will this happen? If I start with A belongs to F, I have to prove that A belongs to KH. That means if I have to prove that A belongs to KH, then I have to prove that every elements of H will fix the A. Every elements of H must fix every element of F. And that is always there because H is a subgroup of GKF. And what is the definition of GKF? GKF is collection of all automorphism which fixes every element of F. So that means already every element of H is fixing every element of F. So one thing is clear, that K is a subset of F is a subset of KH. Okay. So this kind of relation is there between these three fields, and because K is a normal extension of F, dimension of K over F is finite, and hence dimension of K over KH is also finite. So because dimension of K over KH is finite, using this theorem, what I can say is this dimension is less than equals to order of, or dimension of K over KH. Okay. So you can see that partially we have proved this both results. We have proved that order of the dimension of K over KH is larger than equal to order of H. Now we have to prove that order of H is larger than equals to dimension of K over KH. Okay, so one side of this this equality we have already proved, and also we proved that H is a subgroup of GKKH. Now we have to prove that GKKH is a subgroup of H. Okay, so partially both these results have been done, and now we have to prove the other side. For that, we know that what we know, that K is a normal extension of F. K is a normal extension of F. And because K is a normal extension of F, by definition of normal extension, we know that K is a finite extension of F. Yes. So K is a finite extension of F. And because K is a finite extension, we have already proved in last unit that every finite extension is a simple extension. So we can say that K is a, or in fact I can say that K is also a finite extension of KH. That is also true because we know this relation, that F is a subset of KH is a subset of K. So because K is a finite extension of F, I can say that K is also a finite extension of KH, because dimension of K over F is nothing but dimension of K over KH into dimension of KH over F. And because dimension of K over F is finite, we have dimension of K over KH is also finite. So K is a finite extension of KH we have, and hence we know that every finite extension is a simple extension. So I can say that K is a simple extension of KH. Okay. Therefore, by definition of simple extension, what we can write is there is some A belongs to K such that KH of A is equals to K. Right? By definition of simple extension, we can say that K is nothing but KH of some A for some A belongs to K. Because of definition of simple extension, we have this. But this will imply that, see, now K is nothing but KH over A. So we already know that dimension of K over KH is finite, right? So now let us substitute the value of K, that is KHA. Dimension of KHA over KH is finite. Suppose that the dimension, what does this mean? That A is algebraic over KH, right? because we have already proved that A is algebraic over F if and only if dimension of f of A over F is finite. So using that theorem, I can say that A is algebraic over KH. So let us write that A is algebraic over KH. Using the result that A is algebraic over F if and only if dimension of F of A over F is finite. So using that result, I can say that A is algebraic over KH. Now, because A is algebraic over KH, A must be algebraic of some degree over KH. Okay, let us assume that A is algebraic of degree M over KH. Now, if A is algebraic of degree M over KH, A is algebraic of degree, let us assume that it is M, degree M over KH. Then by result, we can say that dimension of KHA over KH is nothing but n. Okay, or by definition we can say that there is an irreducible polynomial. Okay, by A is algebraic of degree M over KH, so by definition we can say that there is an irreducible minimal polynomial of degree M which is satisfied by A. Okay, and by theorem we have that dimension of KHA over KH is nothing but n. So we have both of these things true, that A is algebraic of degree M over H. So what we have, that there is a minimal polynomial of degree M which is satisfied by A, and using the result we have this also. So minimal polynomial of degree M satisfied by A means what? Irreducible polynomial. We know that by definition minimal polynomials are irreducible polynomials. So there exists an irreducible polynomial let us call that polynomial as QX. There exists an irreducible polynomial, say QX over KHX, because A is algebraic over KH, right? So irreducible polynomial will be belonging to KHX. There exists an irreducible polynomial KHX whose root is A and whose degree is nothing but n. Irreducible polynomial QX belongs to this with degree of QX is exactly same as M, and also dimension of KHA over KH is n. This is because we are assuming that A is algebraic of degree M over KH, and therefore by theorem dimension of KHA over KH is nothing but M. And because A is algebraic of degree M over KH, there is a minimal polynomial of degree M which is satisfied by A. Okay, so one more thing here true is that Q of A is equals to also 0. Okay, A is algebraic of degree M over KH, so we will get a minimal polynomial which is satisfied by A of degree M. Okay, minimal polynomials are by definition irreducible. So minimal polynomials are always irreducible. So irreducible polynomial we got which is satisfied by A and whose degree is n. And due to a theorem, we have that this dimension is also exactly equal to n. Okay, so here we got an irreducible polynomial which is satisfied by A and whose degree is n. So now we'll be constructing another polynomial whose degree is larger than degree of QX and which is also satisfied by A. Okay, so for that, let us start with that construction. Let us first assume the elements of H. See, we already know that order of H is less than equals to dimension of K over KH, and dimension of K over KH is already finite. So in H, there are finitely many elements. So let us assume those elements. Let H be exactly equal to sigma 1, sigma 2, and so on up to say sigma H. So that means there are total small h elements in capital H. Okay, and because H is a subgroup of GKF, right? H is what? A subgroup of GKF. So and so the identity of GKF must lie in H. So let us call that this is the identity. Okay, one of the elements should be the identity because this is a group, right? So let us call this sigma 1 as the identity. Okay, so sigma 1 is the identity method. Okay, and here what we have is order of H is nothing but small h. So let us assume that in capital H there are small h elements, namely sigma 1, sigma 2 up to so sigma h. And the first element, let us assume that the first element is the identity element. Now let us construct some elementary symmetric functions. How we'll construct using this sigma 1 of A. See, A already we have, right? Because K is a simple extension of F, we got some A. So that same A we are using here. So let us consider elementary symmetric rational functions of consider the elementary symmetric functions of sigma 1a, sigma 2a, sigma 3a, and so on up to sigma na. So this will be nothing but A, right? Because sigma 1 is identity. So elementary symmetric functions, namely, we know how elementary symmetric functions is defined. Elementary symmetric functions of not x1, x2 up to xn, but this is elementary symmetric function of sigma 1a, sigma 2a, sigma 3a up to sigma na. So what will be the first element? Let us call it as alpha 1. So alpha 1 is nothing but addition of all this. We have already seen elementary symmetric functions, okay, in this unit. What will be alpha 2? Alpha 2 will be product of two elements at a time, that is sigma 1a, sigma 2a plus sigma 1a, sigma 3a, and so on. Okay, up to sigma 1a into sigma na, and then sigma 2a into sigma 3a, sigma 2a into sigma 4a plus sigma 2a into sigma 5a, and so on. Okay, so this kind of elements are there in alpha 2, and so on up to alpha n will be product of n elements at a time. So sigma 1a into sigma 2a, and so on up to into sigma n. So we are considering this elementary symmetric rational functions alpha 1, alpha 2 up to alpha n. Then can you see that it is clear that then it is clear that what that any sigma I of any alpha j is nothing but alpha j. Okay, any sigma I of any alpha j is alpha j. That means every sigma i's are fixing every alpha j's. Okay, why is that true? Let us try to see. There is a theorem that you have already proved, maybe in your bachelor's. Yes, in your bachelor's you have proved this theorem that if you start with a finite group G, if G is a finite group, and if you start with one element of G, then if you consider this set A into G, A into G, how is it defined? A into G for G belongs to capital G. This is how A into G is defined. Then A into G will be nothing but exactly the whole G. That means from a finite group G, if we start with any element, and if you multiply that element with the whole group, then again you will get the group back. Okay, any element. This is true for any A. For any A, this result is true. That means if you start with an element of the group, if you multiply it with the group, you will get back the group. Okay, so using this result, this is true that sigma I of alpha j is nothing but alpha j. Sigma I of alpha j is nothing but alpha j. Let us see why. Suppose we are considering sigma 1 of alpha 1. I have to prove that sigma 1 of alpha 1 is nothing but alpha 1. Okay, so sigma 1 of alpha 1. What is alpha 1? It is sigma 1 of A plus sigma 2 of A plus and so on up to sigma n of, oh, sorry, sigma h, sigma h of A. and that is same as sigma 1 of sigma 1, because sigma 1 is an automorphism. We can do this sigma 2 of A and so on up to sigma 1 of sigma h of A. Okay, and this is sigma 1 composed with sigma 1. Okay, now because we have proved that for a finite group G, A into G is nothing but A. That means, see, suppose the group elements are of this form. To explain this, suppose the group elements are of this form. G is equals to G1, G2, and so on up to G H. Okay, and if you start with any element, say G1, okay, then what will be G1 of capital G? G1 of capital G is nothing but G1 into G1, G1 into G2, G1 into G3, and so on up to G1 into GH. But by the result, this is same as capital G, which is nothing but G1, G2, and so on up to GH. So that means G1 into G1, because both the sets are same. G1 into G1, maybe it is G2. G1 into G2 is maybe, say, it is GH. G1 into G3 is maybe somewhere here. Okay, so that means we are getting back the element. That means G1 into G1 is again an element of G only. We don't know which element, but it is an element of G. G1 into G2 is again an element of G only, but we don't know which element. So sigma 1 into sigma 1 is again an element of H only, but we don't know which element. So maybe it is, say, sigma of 8. Okay, maybe it is sigma 8 of A, and maybe this is sigma 1 of A, and so on. But what you can note is that we will get back all the elements of sigma, or all the elements of H. So this will form, we can write by changing the order, we can ultimately write this is same as sigma 1A, sigma 2A, and so on up to sigma H A. Okay, because sigma 1 into sigma 1 is nothing again but sigma of some J. Maybe it is sigma 3, maybe it is sigma 4. But ultimately, by changing the order, we can get the whole elements back. But this is nothing but alpha 1. So what I have proved is sigma 1 of alpha 1 is alpha 1. Similarly, you can prove that sigma 2 of alpha 1 is also alpha 1. Sigma 3 of alpha 1 is also alpha 1. Similarly, you can prove that sigma 1 of alpha 2 is nothing but alpha 2. Sigma 2 of alpha 2 is again alpha 2. So in short, sigma I, for any I, sigma I of alpha j is same as alpha j for any j. Okay. So that is because of this result that for a finite group G, if I start with an element A belongs to G, then A into G is nothing but G. Okay. So what we have proved is every sigma I fixes every alpha j. So that means you can see that every alpha j is in KH, because what is KH? KH is all the elements of K which are fixed by every elements of H. Okay, and the elements of H are nothing but sigma i's, and we can see that every elements of H are fixing this alpha j's. So every alpha j is fixed by every elements of H. So therefore alpha j's are in KH. Okay, all of these alpha j's are in KH. So if I consider this polynomial, just consider the polynomial. Which polynomial? Px equals to x minus alpha 1, sorry, sigma 1 a, x minus sigma 2 a, and so on, x minus sigma h a. So we are considering a polynomial whose roots are sigma 1a, sigma 2a, and so on up to sigma ha. Okay, then can you see that this polynomial belongs to khx? Why this belongs to khx? Because all the coefficients, may it be 1 here or sigma 1a, sigma 2a, all are in kh. Okay, why sigma 1a is in kh? Sigma 1a see, because here we have proved that sigma 1. Why is this sigma 1a in KH? See, KH is every elements which are fixed by. See, what is the definition of KH? KH is all those elements of K which is fixed by every elements of H. That is sigma A is nothing but A for every sigma belongs to H. Now let us prove that this sigma 1 of A is in KH. Okay, in order to prove that sigma 1 of A is in KH, what I have to prove? That if I start with any element of H, it must fix this sigma 1A. So see, H elements of H already are known. It is sigma 1, sigma 2, and so on up to sigma H. So if I start with any element, say sigma J. So what is sigma J of sigma 1 of A? I have to prove that it is same as sigma 1 of A, right? So this is sigma J of sigma 1 of A. Now sigma 1 of A is nothing but A only. Sigma J of sigma 1 of A is nothing but A only, because sigma 1 is an identity. So or in order to view that, okay, we will not go by this definition. Let us solve this polynomial and then we can see that it is in KH. Okay, right now let us not write the that it belongs to KH. Suppose if we solve this, then what do you get? You can see that it is x to the power h minus alpha 1, x to the power h minus 1, plus alpha 2, x to the power h minus 2, and so on. And the last second element will be minus 1 to the power h minus 1, alpha h minus 1, x, plus minus 1 to the power h, alpha h. Okay. See, you can simplify this and get this. To understand this, you take h to be 3 or 4. Okay, you take h equal to 3 and then you solve this, you will get back alpha. You will get this, and you know that what is alpha 1. If you take h equal to 3, then alpha 1 is nothing but sigma 1a plus sigma 2a plus sigma 3a. What is alpha 2? Alpha 2 is sigma 1a into sigma 2a, sigma 1a plus sigma 1a into sigma 3a plus sigma 2 into sigma 3a. Okay, so you can simply simplify this. We have already seen this in last lectures also. So by taking h equal to 3 or 4, you can observe that this thing is true. So now you can see that this is a polynomial in KHX. Why? Because now it is easier to see that, see here the coefficients are alpha 1, alpha 2, and alpha h, right? All the alpha j's are the coefficients, and we have here already proved that alpha j's belongs to KH, right? So now you can say that this polynomial belongs to KH. It's not that easy to see that this directly this polynomial is in KHX. So by after simplifying, you can easily see that here the coefficients, may it be 1 or alpha 1 or alpha 2, alpha h minus 1 and alpha h. All the coefficients are in KH. Here we have because proved that alpha j belongs to KH. So now you can see that this we have constructed a polynomial of degree h which is in KHX. Okay. Now the interesting thing is that this is nothing but a. So a is the root of px. Okay, and therefore I can say that p of a is equals to 0, right? Now, because qx is the minimal polynomial or irreducible polynomial which is satisfied by a, that is the minimal polynomial which is satisfied by a, that is qx is the smallest degree polynomial which is satisfied by a. So what will be the relation between degree of px and degree of qx? Obviously, degree of px must be larger than or equals to degree of qx. Why? Because qx is the smallest degree polynomial, minimal polynomial which is satisfied by a. Okay, so degree of px is nothing but h, and degree of qx is nothing but m, right? and M was nothing but dimension of KH A over KH. Dimension of KH. See, we are seeing that what was the degree of QX. Degree of QX is nothing but M. M is nothing but dimension of KHA over KH. And what is KHA? It is nothing but K. So dimension of K over KH is nothing but M. So here degree of QX is nothing but dimension of K over KH. Dimension of K over KH. Okay. So what I have proved is H is nothing but order of capital H, right? So order of H is larger than equals to dimension of K over KH. Here we have already proved that order of H is less than equals to dimension of K over KH. And now we prove that order of H is larger than equals to dimension of K over KH. And so order of H and dimension of K over KH is same. Okay, so first part is done. Okay. Okay, so one part we have proved. And already we have proved that, once again you can see here, that we have already proved that H is a subgroup of GKKH, right? So now we have to prove that GKKH is a subgroup of H. So H is a subgroup of GKKH, that is already known. Okay, and now we have proved that order of H. See, uh, what is order of GKKH? See, this implies that order of GKKH is larger than equals to order of H. Right? But here right now we have proved that order of H is nothing but dimension of K over KH. Right? And dimension of K over KH is larger than equals to order of GKKH. Why this is true? Because we have proved that if K is a finite extension of F, then dimension of GKF, order of GKF is less than equals to dimension of K over F. Unit 3 last theorem. Okay, so using unit 3 last theorem, we have this. So we can see that sandwich, it has become sandwich between order of GKKH and order of GKKH. So what we have proved is order of H is same as order of GKKH. Right? So order of this set and order of this set are same. So both the set must be same, because obviously this has finitely many elements. That's why this is. Okay, what we have proved here is order of this set and order of this set are both same. So both the sets must be same because there are only finitely many elements in both the sets. So we are done. What we have proved is H is nothing but GKKH. We are done with both the claims. H is same as order of GKKH. And so we are done with this theorem.